Further control and improvement, Module 6, Lecture 1, Process Reliability. Learning objectives are to explain the difference between reliability and maintainability, to calculate the failure rate, mean time between failure, and availability of a manufacturing process, to compute the reliability of a process, including processes in series, parallel, and hybrid combinations. There's no reading assignment for this module. These notes will serve as the reading assignment. Reliability is defined to be the probability that a machine can perform continuously without failure for a specified interval of time when operating under stated conditions. It's really important in manufacturing and in any process, business process, hotel operation, any kind of process, to increase reliability, because increased reliability in the end results in cost savings and maintaining a competitive edge over our competitors. Maintainability is similar to reliability, but maintainability is actually a characteristic of design, installation, and operation. Usually it's expressed as the probability that a machine can be retained or restored to operable condition within some kind of specified interval of time. So maintainability really depends on our maintenance plan. The two terms are related, but they're not exactly the same. So in order to understand reliability and maintainability, it's important to understand product life cycle. So early on, when products are manufactured, you tend to have a lot of kind of failures really early on, basically just due to design problems. The products aren't exactly designed correctly. There's flaws in design. So you get a lot of early failures on when you're initially developing a product. And then, as you improve the product, the failures decrease, and you kind of reach this flat kind of area in the middle, which is really the longest period of time when the product is actually operating under its specified conditions. So here you're going to have kind of problems with, if you have trouble with manufacturing, you might have trouble sourcing certain materials, like supply chain kind of problems that we've all experienced in the last year. You can also have a case where customers just kind of abuse products, and so you can have products fail from that kind of thing. Near the end of a product's life, you have what's known as the wear out phase. This is the phase where the product just simply wears out. Every product has a finite lifetime, and it's basically based on the design of the product, what the product's made out of, and how a customer treats it. If we have a time-dependent system, we can define what's known as the failure rate, and it's given by the Greek symbol lambda. It's the probability of a failure during a stated period of time, cycle, or number of impacts. This can be calculated as follows: the number of failures observed divided by the sum of the test times or cycles. The inverse of the failure rate is what's known as the mean time between failure. It's simply the reciprocal of the failure rate. Since many systems need periodic maintenance or corrective actions like lubrication, etc., a system's reliability can be judged in terms of the amount of time it is available for use. So this leads us to define a term what's known as the availability, as the mean time between failures divided by the mean time between failures plus the mean time to repair. So let's take a look at a quick example. Let's suppose we have 20 windshield wiper motors are being tested using a time-terminated test. The test is concluded when a total of 200 hours of continuous operation have completed. During the test, the number of windshield wipers that failed before reaching the time limit of 200 hours is counted. If 3 wipers fail after 125, 152, and 189 hours, and the remaining 17 wipers completed the test without failure, calculate the failure rate and the mean time between failures. So here we can simply plug in our formulas. 3 windshield wipers failed. We can divide by the number of hours that it took. So 1 failed at 125 hours, 1 failed at 152 hours, 1 failed at 189 hours. And 17 remained, kept working for the entire time period, so we have to include that in the denominator as well. So we calculate this, we get 0.0008, and I rounded this off. So if you take the reciprocal of this number, you get the mean time between failures is 1,250 hours. So another example, windshield wiper motors are readily available and easy to install. Calculate the availability of the windshield wipers on a bus driven 8 hours a day. If the mean time between failures is 1,250 hours, when the windshield wiper must be replaced, the bus is out of service for a total of 24 hours. So here we can use our formula. The mean time between failures is given, 1,250. The repair time, it doesn't take 24 hours to repair the windshield, but wiper, we're told that it's out of service for 24 hours. So if we plug in our equation, we get 0.98. That's the availability. So how can we calculate the system reliability? Reliability is the probability that a product will not fail during a particular time period. If N is the total number of units being tested, and S represents these units performing satisfactorily, then the reliability is given by the following formula: R equals S over N. System reliability is determined by considering the reliability of each individual component and parts of the system. To calculate system reliabilities, the joint probabilities of their independent failure rates must be utilized. So this sounds kind of technical and kind of confusing, but let's look at some simple examples, and I think it'll become clear to everyone. So first of all, when you talk about systems, you have the reliability of the individual components, but typically, a product is made of more than one component. It's made of products that are hooked together in either series or parallel or combinations of the two. So first, let's take a look at the products that are in series. So a system is in series if it functions depending on where all the components of the system are functioning. In other words, so here we have our system. It's made up of 4 components. So and they're hooked together in this kind of chain. So if this one is taking out of the system, we just cut it here and cut it there and remove it, this whole system goes down. This whole product is not able to function. So maybe this is our television set, and inside the television set, there's our picture tube, there's a power source, there's the electronic components that get the signal in and signal out, etc. So each one of these has a certain reliability. So the overall system reliability is simply the product of each individual reliability. So as a simple example, let's calculate the reliability of the flashlight. So a flashlight works, basically it's in series. You have the batteries hooked here, and so the batteries are in series with the light bulb and the lens and the reflector. So here, all these things have to be functioning. If a battery wears out, well then, the whole light bulb, the whole flashlight doesn't work. So if we're told what the reliability of each individual component is, the reliability of the entire flashlight is just the product of each of these individual reliabilities. So we can just simply multiply 0.75 by 0.98 by 0.85, just multiply all these together, and you can get a product reliability of 0.59. Now this seems kind of interesting to people, because you might say, wow, that's interesting, because each of these has a higher reliability, but that's the whole point of something being in series, is that actually you decrease the overall reliability by putting components in series. The net result is the product gets less reliable. You can only be as reliable as the least common denominator here, and when you multiply these together, we get about 0.59 or 59%. A system in parallels is able to function if at least one of its components is functioning. So here it shows a system in parallel. So let's imagine, for example, sometimes I tell my students to imagine, you have a signal. The signal can come, let's say this is coming in here, going out this way. So a signal can come in this way and go through here in this way, or it can go the alternate path through here, down, and then back. So even if I totally remove R1 from the system, I still have a path for the signal to flow. Same way, if I took out R2, I would have a path for the signal to flow this way. So that's how you know something is in parallel, just by doing that simple analysis. The formula is a little bit different for reliability in parallel. It's given by the following formula, where R1 is one element in parallel, R2 is the next element. This shows we have more than two elements. If we only had two elements in our system, well then these two would be crossed out, and we just have R1 and R2 there. So let's take a look at an example of two elements in series. Let's say we have a twin engine aircraft with two alternators that support a single electrical system. If one of these were to fail, the other one would allow electrical system to function. So that's how we know it's in parallel. These alternators each have a reliability of 0.92. Calculate their parallel reliability. So again, we plug in the formula, and we can calculate this as 0.9936. So here you can see the advantage of products in our systems in parallel, because even though each individual alternator has a reliability of 0.92, the overall combination has a much higher reliability. You can also have reliability in backup systems, like a lot of batteries have a spare backup. So for backup systems, we rely on this formula here. R1 is the reliability of the primary product, and RB is the reliability of the backup. So typically, if you have a battery and you have a battery backup, R1 is the battery and RB is the backup battery.